Let's get started with lab 1 on the checkout process simulation. So we are given a task to model the checkout of a store, and then we are also going to model what happens if we add some self-checkout counters. Okay, and we have to do this for a base checkout model where the arrival rate for customers is 20 per hour. And then we have to do it for 25 customers per hour. And then we do the self-checkout option. So that's what we have to model. And we're given some data on how many items the customers purchase. Now, why is that data important? Because if we skip this note for a while, this is an aside, and we look at the checkout model, okay, the checkout process takes 10 seconds to process each item purchased by a customer, plus a fixed time of 2 minutes, maybe to make the payment to the cashier. And so in this service, our cycle time, or the time to process this step, that time is not fixed. So in the examples you might have seen before, we knew the cycle time of each step. Okay, this step takes 5 minutes, this takes 4 minutes. But now we have a process where the time taken depends on how many items did the customer purchase. Because number of items times 10 seconds plus 120 seconds for 2 minutes is how long it's going to take in seconds. Okay. So that's what makes this tricky on how are we going to model that. And we also know that the number of items purchased by the customer is going to be modeled by negative binomial distribution. And we have to estimate the parameters of this distribution given a data on the items purchased by the customers. Okay. So you can read this note on negative binomial distribution. It's a very useful distribution whenever you have data which cannot be negative. So like number of customers arriving or how many items were purchased. And we prefer the Poisson or the negative binomial in those cases because the normal distribution, which is very popular otherwise, can actually go negative. So let's say you have a mean of 10 and a standard deviation of 8, and you generate a normal random variable, you will get negative values like -2, -5, because these negative values are close enough to the mean of 10 that there's a probability, a non-zero probability that they will be generated. Whereas with Poisson or negative binomial distribution, they will not generate negative values. They only generate positive values. And they also kind of look bell-shaped. And so, for like bell-shaped distributions, we can use these instead of the normal distribution. Now, Poisson distribution has a strong assumption that the variance of the data equals the mean. And if that is approximately true for our data, we can use the Poisson distribution. A lot of real-life data is over-dispersed. What it means is that the variance is more than the mean. And then you cannot use the Poisson distribution, but then you can use the negative binomial distribution. Okay. So in the negative binomial distribution, M is the sample mean, S squared is the sample variance, which means S is just the sample standard deviation. So if you have the sample mean and the sample standard deviation, you can calculate this parameter, which is called theta or K or R. This is the shape parameter. It defines the shape of the negative binomial distribution. It's going to look kind of like Poisson, or it's going to look a little bit flatter and wider. And then the other parameter you need, which is P, can also be estimated by dividing the sample mean by the sample variance. Okay. So here's a plot showing us the distribution. These blue bars are the negative binomial distribution. And we can see for small values of K, which is the shape parameter, this R, which is also called K, also called theta. So for small values of R or K, our distribution, the negative binomial, is very different from the Poisson. Poisson is in red. Okay. As K goes up, it becomes closer and closer to Poisson. K increases when the standard deviation squared, the variance here gets closer to m. If the variance is much bigger than m, then the denominator will be a big number and you get a small value of k. So this would be the case where you have over dispersion. You can see there's a long tail. So, sometimes you get these large values. And if you don't have over dispersion, that means the variance is just slightly above the mean. So very close. So you get a very small number in the denominator and you get a large value of k, something like this, where you can see that we've almost become Poisson because there's no over dispersion. The variance and mean are about equal. So let's look at the data given to us. This is the data given to us. Okay, we have the items purchased per customer for a bunch of different customers. And we can calculate the mean and the standard deviation and I guess then the variance of the sample of data. So the mean in Excel is calculated using the equals average function. Okay, so we do equals average, and then we select this data. I can press Shift Control down arrow to go all the way down to the last data point, and then press Enter. It will add the closing bracket itself, and it'll give us that the average number of items customers are buying on a trip is about 20. Then you'll find the standard deviation .s because it's a sample of data. So the sample standard deviation, again, Shift Control down arrow to select all the values, and that's about 10. So if I calculate the variance, that's just the standard deviation squared. So I do this hat symbol, right? I do this, do Shift 6 to get the hat symbol, type 2 to raise to the power 2, and I get a variance of 104. You can see that the variance is much larger than the mean. So we have over dispersion. Okay, data is too dispersed, so we need to use the negative binomial distribution. We cannot use Poisson. So for that, we're going to calculate R, the shape parameter, and the P. Once we have these parameters, we can generate values of the negative binomial distribution in our simulation and simulate customers with average of 20 items purchased with a standard deviation of 10, and it will have a bell-shaped type of shape. Okay. So if you go to a write-up, we're given the formula. So mean squared divided by variance minus the mean. Okay, so this is going to be at the top, we get mean squared, divided by, at the bottom, we get the variance, which is s squared minus the mean. Okay, so that's 4.67. So if we go here, this is the plot for k is 3, this is for k 7.5. So our distribution is going to look somewhere between the first and the second plot. So it's going to have this thick tail and a little bit narrower than this one. So it's going to be between the first two figures. So quite different from Poisson. Now for P, the formula is mean over the variance. Okay, so we take the mean divided by the variance. So that's our P value. So we will use these two values in our simulation model to simulate how many items a customer is carrying. Now let's go to Anylogic and build this. Okay, so we're going to create a new model in Anylogic, and I'm just going to call it lab 1 video because I'm recording a video. I'm going to set the model time to hours. Okay, why? Because if I look at my model, I need to run it for 100 hours. Okay, and I'm given the arrival rates in 20 per hour, 25 per hour. Obviously, I can set it to minutes and just change the arrival rate. If it's 20 per hour, that means it's going to be 20 over 60, about 1/3 per minute, 1/3 arrival per minute. So I could do 0.33 per minute. So I could still convert everything into minutes and set this to minutes, but I'm just going to keep hours so that I can enter these values exactly without having to convert them. Okay, so let's do that. Okay, Now I'm going to set the zoom level to 200% because for me, at 100% things are too small. It totally depends on your screen resolution. So if 100% is good, it's large for you, that's great. If you have a high resolution screen, 100% might be, things might look a bit small, so you can set the zoom level to 200% or 150%. Okay, now the first thing I'm going to do is I'm going to set up this simulation setting so I don't forget. So change the random seed to 42, which is going to initialize a random number generator so that your results will match mine if we set the same seed. And we're going to set the simulation to run for 100 hours. I go to the projects area, I go to simulation main, and here I can say stop at specified time and after 100 hours, and then the fixed seed will be 42. Okay, so we don't want to say random seed here, so let's pick a random value, but the seed for the random number generator should be 42, so we set that here because it's given in the instructions. Okay, now we can get started with building our model. So the first thing we need is a source block that's going to have our agents arrive. Actually, even before that, we need to do a little, we need to do something, or you could do it later too, but let's start with that. We can't just have agents arriving and going through the system, like just put, for example, process modeling library, just put a source block, right? And then just go on, because it's going to create a default agent that will be the customer flowing through the process. And the default agent has no property or parameter to tell me how many items that agent bought. So I need to have a type of agent which can store within it how many items it purchased. So at the checkout time, the cashier will know how long it takes the cashier, to process this agent or customer. So to do that, we can drag the agent type here to create a new agent type. Create the agent type from scratch. That's good. And I'm just going to call it customer because it's going to represent my customer. And you can just leave the defaults here. You're going to add a new parameter. Let's make it int, an integer, because people generally don't buy like 2.5 of something or 3.5 of something. Now, we are not modeling if they buy stuff which sells by weight. We're just saying how many different items, because the assumption is even if you buy something by weight, it takes the cashier the same amount of time to check you out versus you bought something that is not by weight, or approximately the same, so we don't have to make that distinction. So this is where you have to experience with simulation can help you, because somebody might say, oh no, to model this customer in this process, I need to know how many items he or she bought by weight, how many items they bought, which is you can just scan them, and then I'm going to have, let's say, 6 seconds to process an item which just gets scanned, and maybe 12 seconds to process an item which is going to be sold by weight. It has to be weighed. And the question is, do we need this complexity? If we just take the average time, we can just measure, we can just stand near a cashier and measure the average time taken. Is it enough? Do we need to treat items by weight and other items separately? So sometimes a lot of added complexity doesn't really change anything for you, doesn't give you any benefit. And so it's better to keep things simple, but not so simple that they oversimplify the reality. So just having an average value in terms of how long it takes to process an item at a checkout cashier probably is sufficient. At least we're going to start with that. And then if we feel that our time to check out for different customers with different items is not really matching reality, then we can adjust these parameters. So we're going to add a parameter which is integer. Its default value, we can make it 0, and its name is going to be num items, number of items this customer is buying. Okay, so you see that it created a new tab called customer, and it has a parameter called num items, so the default value of 0. So when you go back to our simulation, this source block is going to generate customer agents to put them into our process, not just regular. So after the source block, we need to have two cashiers. So we're going to model the cashiers by delay blocks. Okay. And each cashier has their own queue before it. So each cashier gets a queue. So we drag a queue block. I can drag a box here at the center. I can click that and move this around. Okay. So let's call this, let's name this delay block cashier 1. And let's call this delay block cashier 2 because we have two cashiers. And then this is going to be a queue for cashier 1, so I can just call it Q1. And so this, look, I already have Q1 here, so I'm going to call it Q2 for cashier 2, and this one here for cashier 1 is going to be my Q1. Okay. And now the source block is going to send customers into these queues and then the cashier ahead of the queue, after the queue, right? But which queue does the source block send the customer to? It's going to be the one which has a smaller queue because customers will self-select and they would like to go to the cashier who has a smaller queue. Okay, so we need the select output block. Okay, that is going to allow me to route incoming agents either through this node to the right or to the bottom node. So I can put it right here. Okay. And let's just rename it to like select cashier. Okay. And then I'm going to take this, double click here on the bottom port, go down, go right, click on the green circle and connect that here. And then the source block will be connected right here. So what we have to do is route the incoming customer to whichever of the two has a smaller queue. Now, there's multiple ways to do that. One is you can just have a probability of 50%, 0.5. So on average, half the customers go here and then half the customers go here. And on average, that will be equal load on both the cashiers, right? But here's the tricky thing. When you have people with different number of items, it can get tricky. Because if you send to Q1 and cashier 1 a person, let's say you get a person like 50 items in the cart, a big order, and they kind of block up cashier 1 because it takes a long time to check them out, this queue will start to grow. And if we have a 50% probability, we'll still be sending a lot of people in this queue, where we should be sending people to the other queue. So instead of the probability for this select cashier block, we're going to do if condition is true, and we're going to give it a condition. Okay, and the condition is going to be q1 dot size. Okay, that's the how big the q1 is, QUEUE1. That's the name here, q1 dot size. If it's less than q2 dot size, if this condition is true, it'll go to this to the right here, and if this condition is false, that Q1 is actually bigger, it'll go to the bottom, it'll go to Q2. Okay, and we want to say condition is stochastic or volatile because the queue sizes are changing. So for every customer that comes to this block, you want to run this code again and figure out which queue is the shorter for at that time, because the queue lengths are changing over time. So this way, the source block generates the customer. We come here, we check the queue sizes, we go to the cashiers, okay, and then after the cashiers, we're just gonna check out. So we're gonna go to the sync. And we can join this, double click here, go up, click here, go here, and click on the green block, and here we go. So you can go to the sync, okay? Now this simulation should run right now, but it's not complete because we don't have the delay time specified, okay? So what should it be? It's right now just set to 1 second and just 1 second on average with the triangle distribution. We have to change that based on the number of items, but we're just gonna run it to see if our routing is working. So you can see that, you know, both of the queues are getting people. However, you'll notice that a lot more people are going to Q2 than Q1. We should be getting about equal because at currently our time taken at the cashier is the same because every customer has 0 items. We didn't specify how many items each customer has, right? And so if you notice that we got much fewer items in Q1 and a lot of them in Q2. The reason is because everything is the same here forward. A lot of times the queues are equal. So what happens if the queues are equal? Then Q1 size is not less than Q2 size, so they don't go to the right. When both queues are equal, we just send them to the bottom. We don't want that. If both queues are equal, then they should not always go to the Q2. They should sometimes go to Q1, sometimes to Q2, right? Because if you're a customer and you see 2 queues are equal, you're not always going to join the queue on your right. Sometimes you'll join the one on the left, sometimes on the right, like as customers come in and see equal queues. And so we can leave it like this for now, or what we can do is we can make this code a little bit more complicated. And the way we do that is this. We check if the queues are equal first. Q1.size equals Q2.size. Put a question mark. If that is true, then just flip a coin. Uniform function returns a random variable between 0 and 1, a uniform random variable. If it's less than 0.5, that's like flipping a coin for heads. So we flip a coin if the queues are equal, and if they're not equal, then we check which one is smaller. Q1 is smaller, we send it to the right. So that's a more complicated condition. I'm going to show you again. Q1.size. Equal means if it's equal to Q2.size, question mark, what to do then? If the both queues are equal, flip a coin. Uniform less than 0.5 is flipping a coin on where to go. So if it's false, it'll go to the bottom. If it's true, it'll go to the right. So if the queues are not equal, then check if Q1 is smaller, then send to Q1, else Q2 will be smaller, then send to Q2. So this condition takes care of the case when they're not equal. And now, if you run the simulation, you can see that the queues are almost equal. So our select cashier function is working properly. As customers come in, they're being routed based on queue size. And when the queue size is the same, they're getting about equal customers to both cashiers. So our routing logic seems to be working. Now we need to figure out the delay function here. Okay, and that's kind of the complicated part, because what we have is that cashiers take 10 seconds to process each item, and then 2 minutes of extra time above that. So if I go here, I can type in, okay, agent.numItems, because that's the property of my customer, numItems, that has the number of items. And whenever a customer is in a block, is just referred to as agent. So agent here is the customer that comes in at this particular time. So agent.numItems start 10 seconds plus 120 seconds is the time cashier one takes in seconds. See, we have the units in seconds. Okay. And then cashier 2 is going to be the same, agent.num items star 10 seconds per item plus 120 seconds fixed time. Okay. And now if we run our code, we have an error. Let's see what happened. Okay, so our queues here have a very small capacity, and we are getting an arrival per second. So when this takes hundreds of seconds, we're getting like 60 customers per minute arriving, which is incorrect because we didn't set the properties here properly. So if you look at our arrival rate that we have to use 20 per hour. Okay, so we set this to 20, and this is per hour, not per second. Okay, so that should fix it a little bit. So now you can see that it's taking some time to do the processing at the cashier, and the queues are still about equal. It's basically taking 2 minutes at each cashier because the items are still 0. We haven't built that logic in that each customer has a different number of items based on the negative binomial distribution, but our routing is working, our queues seem to be working, and so on. Also, because we don't know if 2 cashiers are sufficient, our queues may grow longer, so it's worthwhile to set the queues to maximum capacity. And then we'll see if the queues start to get too long, we can add more cashiers, we can add checkout counters, we can then modify the system. But right now I'm going to set the queues. It's very common in the beginning of a simulation to set the queue capacity to unlimited and then see, and if the queues get too longer, then you can adjust the capacity of the system. You could also set the queue size to be equal to, let's say, 100, because that's how much space you have, and that's also fine. Then it'll tell you when the queue gets full, this will not be able to send an agent here, and it'll give you an error that, oh, I can't push agents through because the queue is full. That was the error we were getting earlier because our arrival rate was set too high. Okay, so our arrival rate set properly, our routing is done properly, our cashier time formalized properly done. One thing I'm going to show you to do is, instead of hard coding the 10 seconds and 120 seconds, it's better to go to create some variables from the agent palette and save that 10 second and 120 seconds in variables. Because what if our model got more complicated and at other stages in the model we had to use the 120 or the 10 seconds, and then later on the boss said, okay, we trained the cashiers or we gave them some equipment, now they can scan faster, so rerun your simulation. We have to go through the model, find everywhere we use the 10 seconds and 120 seconds and manually change them. So that can get very cumbersome. So we're going to save all these settings of the simulation, like how long it takes the cashier, in variables. So we'll call this variable cashier fixed time. Okay, and that just needs to be an integer. There's no decimal values required. That's 120 seconds. Okay, and then I can drag another variable and I can call it cashier item scan time, something like that. So time to scan one item, that's going to be an integer, and that's going to be 10 seconds. Okay, now I'll use these variables to set the delays, and then in future, if somebody says, hey, what if the cashiers can scan an item in 8 seconds, I just change this to 8 and it changes everywhere in the simulation wherever that time needs to be used. So I'll go to cashier 1 and I'll say, agent.num items times cashier item scan time, and plus, instead of 120, I'll say cashier fixed time. And the same thing needs to be copied into cashier 2. Okay, and now you'll see that simulation still works, and if I need to change these values, I can just change them in one spot, and everywhere in the model they're used, they would change automatically. Okay, so what we need to do is now make sure that the customer has the num property set. So I'm going to use this block, this action at exit, Remember to not use onExit, but at onAtExit, because what onAtExit does, it does what you tell it to do before the agent leaves the source block. So it works on that particular agent. And so when the agent comes here or here at the next block, you can immediately use whatever you set here. OnExit works a little bit differently and it's a little bit tricky. So onAtExit is what we need to use. So onAtExit, we need to generate a negative binomial random variable. And that will be the number of items. And then we assign that to agent.numItems. So we say agent.numItems equals, okay, and we do negative binomial, okay, and then you have to give it the P and the R values, okay. Put a semicolon at the end because that's how, you know, this is a whole statement, so it ends, it needs to end in a semicolon. So what are my P and R values? In Excel, I already calculated the P and R values. My P is 0.19 and my R is 4.676. So 0.19 and 4.676. Okay. Now, this would give me a number with fractions. I don't want, like, you know, 3.62 items purchased. I want 3 or 4. So I'll do math.round to round the result to the nearest integer, okay? And because negative binomial is going to generate something that's not an integer, I'm going to write integer in brackets to convert the result into an integer value. So let's run it now, and you'll see that these different number of items are flowing through the system. Okay, how do we know? Well, we can do something else. We can kind of see what is the number of items that customers have in each cashier. Okay, so to do that, we want to go to the analysis palette and drag a statistics block. Okay, and we can call it num items cashier 1. Okay, and then in cashier 1 on enter we can say, well, first of all, the statistics block is gonna be do not update data automatically. It's gonna be set whenever customer goes to the cashier. Okay, for some things like queue length, you can say update data automatically and just give it the name of the queue size parameter, and it'll just sample the queue size at different times to build an average value of the queue size. Okay, this is a nice way to collect various statistics about your model. But here, I only wanted to add a value when an customer goes to a cashier. Okay, so we'll say do not update data automatically, and it's just discrete data, it's not continuous samples. And then at cashier 1 on enter, we can say num items cashier 1. Okay, and then we want to do agent.numItems. So we want to save the number of items for that customer into the statistics block to keep track of it. And then we can do another one for the second cashier, items cashier 2, and do not update automatically. And then here on enter we can say num items cashier 2 dot add agent dot num items. And now we should be able to see how many items. So you can see the average is around 18, 19, or 20. So our source block is generating the number of items with a mean around the mean of 19 that we wanted it to generate. That sometimes the queue builds up a little bit, then goes down. And you can see that the cashier takes different amount of times for each customer. I'm going to show you another way on how you can verify that your logic is working by displaying some information on this simulation flowchart. Because when we add things to the statistics blocks, it just shows us the mean and it saves all the data, which perhaps we can do other stuff with it. But if you just want to see whether cashier 1 and cashier 2 are getting customers with different items or not, we can go to this display area in our blocks that are available, right? So this one is called presentation, actually, presentation area. And we can take a text item and drag it, put it right here. Okay, I'm going to name it cashier 1 label. It's a label for cashier 1. And I need another one for cashier 2. And I'm going to call it cashier 2 label. Okay, and now I can set the text of these things based on the number of items that the cashier is processing. So you can notice that these text blocks have a property called text with a capital T. And in the cashier block on enter, I can actually set this property. I can say cashier 1 label dot set text, and I can say checking out in quotes, because that's a string, with a space, plus agent.num items plus space items. So this will make a label called checking out, then a number, which is the num items is processing, and then a label items full stop, and I need to put a semicolon to make sure that it knows that this is a separate line, this is a separate line of logic. And then I can just copy this into cashier 2 and just change cashier 1 label to cashier 2 label. Okay. And the plus sign is going to add this text with a number to it, append a number to it, and then append this text to it. Okay. And now, hopefully if I did this correctly, oh, did I not set the name properly? Cashier 2 label, cashier 1 label. Oh, I misspelled cashier, so that was the error. Cashier, and then I can copy paste it. I misspelled here too. I called it chazier, which is wrong. It's cashier. Okay, so hopefully it works now. So you can see checking out 8 items, 27, 9, 10, 15, right? Checking out different number of items for both of them. So we know that our logic of generating customers with different items they buy is working because the cashiers are checking out customers with different items, taking more time. You notice whenever there's a large customer, like a customer with many items, the queue starts to build up, right? The queue goes from 1 to 3 to 2. And whenever we take out small number of items, the queue goes to 0. We go through faster. Okay, so our simulation is working so far. We have modeled the Q2 cashier system, and now we just need to get some statistics on the queue sizes, on the times, and then we'll be done with part 1, and then we'll just have to add the self-checkout counters to do part 2. Now, to display the queue length and the cashier utilization is relatively easy. We can go to Analysis and add a bar chart that we will set to the queue length, the average queue length for Q1 and Q2. So first up, we can make it work. We can keep it vertical, or we can make it horizontal by clicking the bar's direction. So let's make it horizontal. And then I'm going to click and drag the corner to make the bar thinner and also a little bit smaller. And for the title, I'm going to call it Q1 average length. Okay. And then its value is going to be based on the statistics collected by this Q block. Okay, So I'm going to call it, I'm going to get the statistics on the size property of the Q block by saying Q1 dot stat size dot mean. So give me the average value of the size statistic from Q1. Okay, and the stat size is a property of the Q block, and then it has a function mean to give us the mean value. It doesn't mean that every single block here is going to have a stat size property, but we know that Q blocks always do. And let's now need to repeat this for Q2. So let's get another bar chart. Make the direction horizontal, adjust the size however you want. Okay, and the title is going to be Q2 average length. And then again here, Q2 dot stats size dot mean should give me the average Q length. So now if I run my simulation, it's showing me the average length so far. So right now the average is 0.6, 0.5, 0.5, so the same average length. And if you want a simulation to go faster, you can click this plus button, speed up, right? And if you want to just zoom through to the end of the 100 hours, because we're running the simulation for 100 hours in our settings, we choose that. Just click this button, it just jumps to the end, just does the simulation as fast as it can. And you can see that at the end of the 100 hours, our average queue length is about 1.5 here and about 1.5 here. So both queues have on average 1.5 people in them, which means half the time they're like, sometimes they have one, sometimes they have two people in them. Sometimes they may also have 0, sometimes they may also have 3, and so the average comes out to 1.5. So I'm just going to line these up a little bit better. So they stack vertically, and they are the same length, so they look nice and neat. Now I need the utilization of the cashier. So again, I'm going to show that using bar charts. I'm going to make it horizontal. Okay, and make it smaller. Okay, so this one is going to be titled Cashier 1 Utilization. Okay. And I'm going to just set it to the cashier's utilization stats. So I'll say cashier1.stats utilization, okay, and dot mean to get the average utilization. Okay. And the delay blocks have a property called stats utilization that we can use and get the average value and set that equal to this bar chart. And then I'm going to do the same thing with cashier 2, make it a horizontal bar chart, adjust the size to what I want, drag it down to line things up, make them look nice, and then give it a title of cashier 2 utilization. And then again, I'll go to cashier 2, tap into the stats utilization property, get the average value. Okay, and so now when I run my simulation, right, I can just run to the end, and over 100 hours, our utilization is about 87% for the two cashiers. Queue length on average is 1.46, 1.48. And if I go to my assignment, I can fill out for 20, because my arrivals is set to 20 per hour. I can fill out average queue length for both cashiers. I can fill out the utilization for both cashiers. And all that's left is the average waiting time for each cashier. How much did the customer wait before they can access the cashier in the queue? So waiting time in the queue. And once I'm done with that, then I can just change my source block to have a higher arrival rate, and then just copy these, run the simulation and just write down the stats here, and I'll be done with my base model. So we're almost done here. So let's get the queue time. Now Anylogic does not have a built-in property for the queue block, which just tells me how long each customer spends in. So I'm going to have to add some timing block, time measure start and end blocks before and after the queue. And these are in the process modeling library right here. Time measure start, time measure end. So we start measuring time before we start the queue. I'm gonna name this block just TS1. Okay, and now the name just went all the way to the left here. I'm just gonna drag it on top. So I know this block is called TS1. And then I'm going to do time measure end, stop my stopwatch when the customer walks out of the queue. I'm going to call it TE1, time end, or stopwatch ends here. Okay, so this is when I turn on the stopwatch, customer goes in, customer comes out, I stop the stopwatch, and I do this for every single customer so I can measure the time that they spend in the queue. However, right now, time measure end does not know what is the starting stopwatch to link to. And so here, time measure stopwatch, I have to click this plus button and choose TS1. So now TS1 and TE1 are linked so that T1 will mark the end of the time that was started by TS1 on the customer that's flowing through it. Okay, and now we have to do the same thing for the second queue. So I put another time measure start block here. I'm going to call it TS2 because it's on my cashier 2's checkout lane. Okay, I'm going to move the label on top of the block. I'm going to put time measure end right here. I'm going to call it TE2. And then I'm going to click the block, click this label, move it to the top of the block. Okay, and now I have to link T2 to TS2. So it's showing me TS1 as well, but I need to link to TS2. If you link to TS1, you'll make a mistake. So TS2. And also the data set capacity is only 100. I have like 20 customers arriving on average for 100 hours. So I need at least 2,000 on average, and it could be more than that. So I'm just gonna make it, we could make it like 5,000 or 10,000. I'm just going to make it 10,000. If your computer starts working very slowly, you have memory issues, you can just make it like 2,000 or 2,500, something like that, or 3,000. But hopefully my computer can handle it. 10,000 is not a big number for computers to store 10,000 values. So I'm going to make the data set capacity this much so it can save the data on the time of that many customers passing through it. Okay, so link to the start block and set the data set capacity. Now I need to actually take out the value, the average value of the time. Okay, and so that I need to add 2 more bar charts because I like to display the value in a bar chart. I mean, you can display the mean value using a text block as well, like we're displaying here. Processing, checking out how many items. You can just put a text block and display the mean there. But I like just the bar chart to do it. So I'm going to the analysis tab, which has the bar chart, and let's maybe put it up here. We have some space. I'm going to make it horizontal. Or maybe I can just put it here. Okay, the title is going to be Waiting Cashier 1 or Q1 Waiting Time. Okay. And then the value we could take, TE1, which is the time end for the first path here. We're going to take T1 dot, and then I'm going to take the data set value. Remember that this one had a data set right here, data set of 10,000. So I can tap into that data set, say dot data set, and I can say get Y mean, okay. And that will get me, because the data set is going to show an X value and a Y value. X might just be like the number of the customer or something. And then the Y value is going to be the actual time. And I need to put a dot here. So TE1.dataset dot get y mean. That'll give me the average time. Now, there's a little bit of a trick here because in my project, my simulation is running by the hour. It runs for 100 hours. So the default time units in my simulation are hours. So what this is going to give you is the waiting time in hours. But to me, because the customer is probably not going to wait like 3, 4, 5 hours, he's probably going to be waiting some minutes. So I'm going to multiply it by 60 to convert the hour. Let's say it's like 0.05 hours. I want to see it in minutes. I don't know what's 0.05 hours. So I multiply by 60 to convert it into minutes. You would not need to do that if the times units, the default time units of your simulation were minutes. But then if they were minutes, then you would need to change the stop time to 100 hours, which is times 60 to convert it into minutes. You'll need to convert the arrival rate into minutes, which is 20 per hour right now. So when you make your model, you have to pick the time units carefully. I like to pick hours, and then when I get a data in hours, I like to convert to minutes then versus picking minutes and then converting a lot of things to hours. But it's totally up to you. All right, so because I picked hours, I'll get it in hours times 60. That'll convert into minutes, okay? And then I need another one for TE2. So I go back to my analysis tab, pick another bar chart, make it horizontal. I have to change the color to green. Okay. And the title will be Q2 waiting time. And then I'll set it to te2.dataset.getYmean and multiply it by 60. Okay, let's see if I set everything up correctly. So now you're getting all the stats that you need to record for the basic case of 2 cashiers with 20 customers arriving per hour, with negative binomial distribution being used to assign number of items. You can see the number of items is changing. Let's go to the end of the simulation, and I can see my average queue lengths are 1.46, 1.48. My utilizations are 0.88, 0.87. And my waiting times are 8.71 minutes and 8.99 minutes. So a little bit less than 10 minutes is the waiting. So we are doing very fine when the customer arrivals are 20 per hour, right? And we can put all these 6 values, can be put into this table in this column to record your answer. And then you also need to take a screenshot of this window. Okay, in Windows, we do that with this sniping tool. Where you can press plus and you can take the screenshot, okay, and then you can do copy here and then paste into Word, and you can type those values in the table, and you are done with arrival rate of 20 minutes. Now we have to do the arrival rate of 25 minutes. So that's very easy. We can close this window, go back to Anylogic, go to our source block, simply set the arrival rate to 25 per hour, and just hit play, just rerun the model. And that is going to tell us what happens when our customer arrivals go up a little bit, okay, and they go up to 25 arrivals per hour. So let's go to the end of the simulation, and wow, look at our queues, they're blowing up. The average length of Q1 is 82.79, Q2 is 82.78. The utilization of the checkout counters is 100%. They get no idle time. And look at the waiting time, 376.49. Wow. Because 360 minutes is 6 hours, so more than 6 hours customers have to wait here. So notice that how the system was working so well at 20 arrivals per hour, and how suddenly at a sustained arrival rate of 25. Remember, if our arrival rate went to 25 for a little bit and came back down to 20, we'll still be fine. But if we sustain it hour after hour, we're getting 25 people coming in, our capacity to handle them is not enough. That's why the queues are blowing up, queues are growing. If you run the simulation again, you'll notice that the queues start out empty, Notice the queues are 1.2 and going to 2. So the queues are going to grow with time. 3, 4. That means more customers are coming in and fewer customers are leaving in the 1 hour than are coming in. Because 25 customers with those items, we can't check out all 25. So queues are growing. This is how you see a system is blowing up, right? Queues are growing, waiting times are growing. The bar goes down because it resets the scale. Look at the scale, 0 to 20. When you get to a queue length of 20, it will reset the scale of the bar chart, so the queue will appear to fall down. You see, it's still at 20, but the scale reset up to 40. So it automatically resets the scale of your bar charts, which is why you feel the bar chart is getting smaller. It's not getting smaller. And your queues are blowing up. Look at the numbers, okay? We still have about 20 items per customer, so it's not more items per customer, it's just more customers. And everything is just blowing. It's going to keep blowing up, queues are going to keep growing. And if we didn't start a simulation in 100 hours, it'll just keep growing because we are totally out of capacity with 25 customers per hour. So this is the beauty of simulations. You can start with the base case and then increase the demand or load on your system till you see the system break. Like this is breaking right now. It's blowing up. The queues are just continuing to grow, right? That's the beauty of simulation. You can find that breaking point and then say, okay, how much capacity do you need to add to bring the system back down to a stable system with reasonable waiting times? And so you can do all of that analysis just by changing the parameter and rerunning the simulation. That's the beauty of doing these process simulations, okay? So yeah, so you can see that queues continue to grow, waiting time continues to grow, and so we are in trouble with 25 customers arriving. Which is why we are going to, and now you can put in those stats, 6 hours of waiting, an average queue length of 87 at the end of 100 hours, and 100% utilization. You can put those stats in here, and then we're going to see if adding self-checkout counters will help or not. Okay, that's going to be the next part where we need to extend this to allow for self-checkout counters. And there's some restrictions though. Okay, so since the self-checkout kiosks don't have too much space, they're recommended for customers with 10 items or fewer. However, only 80% of customers, 12 items or fewer, it should be 12. However, only 80% of customers with 12 items or fewer take the self-checkout option. Okay, and so we'll have to see if a customer has 12 items or fewer, and then 80% of those customers will get routed to the self-checkout place, and then they will self-checkout, and then we'll see what's the effect on our model for 20 customers per hour. We're already fine, so we don't really need the self-checkout help at 20 per hour, but we'll really want to see if it helps out in this case with 25 customers arriving per hour.